Hello and welcome to chapter number 1, The Essential Ideas. This matches up to the Stax textbook. I hope you've printed out your slot notes and you can fill them in as we go along. In the first section, section 1.1, Chemistry and Context, we'll talk a little bit about history and a couple of things in chemistry, but our main objective of this is to define and apply the scientific method. As we work our way through each chapter, I'm going to cover each section, and what you'll find is I'm going to give you some background information, and then we'll do some practice problems, and those practice problems will match up closely to what you're going to find in your homework and close to what you're going to find on your tests. So using your slot notes as a study guide is a great idea. So let's go ahead and start, and we're going to take a look at chemistry. It's the science of matter, and it's especially chemical reactions and composition and structure and properties of matter. And in Chem 111, we're going to basically take a look at what's happening in chemistry. And then in Chem 112, what we do is we come back and take a look at why it's happening. A lot more math in Chem 112. Chem 111 is a little bit less math, basically some algebra 2 at max. And we're just trying to describe what's going on at the atomic and molecular level. Okay. Chemistry can help us explain our world. It's called the central science. It's the foundation for many other disciplines like engineering, health sciences, pharmacy and pharmacology, science literacy, which is basically investigating the world and trying to find out how it works. So we're going to go back and we're going to take a look at the study of matter. And of course, matter is anything that has mass and takes up space. They're made up of tiny particles called atoms. In the future chapter, we're going to take a look at the history and how we know that it's made up of atoms. And then we're going to take those atoms, we're going to combine them together to form molecules or ionic compounds. And then once we get enough of these molecules or atoms, we can see them, and it becomes macroscopic. But in chemistry, we're interested in what's going on at the microscopic world, even though we can't see it. And we have some really interesting ways in order to see what's going on, or at least imagine what's going on at a very tiny scale. So here's a representation of the macroscopic and the microscopic. On the left, you got a glass with water on it. In the right, you've got the model of water, H2O. And we'll take a look at this model in closer detail towards the end of Chem 111, and we're going to figure out where these bond angles are coming from, and the length of bonds, and a couple other things. So let's take a look at, it says identify each of the underlying items as part of either the macroscopic domain, the microscopic domain, or the symbolic domain for chemistry. Okay. For any in the symbolic domain, indicate whether they are symbols for a macroscopic or microscopic feature. So you'll notice this has the number 4 in the upper left-hand corner because this matches the problem number 4 at the end of the chapter in your textbook. So when I go to do these problems, I've picked them from the ones at the end of the chapter. Your homework are also problems that are picked from the end of the chapter. And I give you a number so you have some sort of reference to go back to. Okay, so let's take a look at the mass of a lead pipe is 14 pounds, and we're looking at the lead pipe. What's underlined is what we're interested in. And if you'll notice, that's macroscopic because we can see a lead pipe. Okay, the mass of a certain chlorine atom is 35 AMU, and we'll talk more about what that AMU means in a couple chapters down the road. So it's microscopic. Okay, a bottle with a label that reads AL contains aluminum metal. And that's symbolic. It's macroscopic because it's representing a single aluminum atom. And the AL, instead of writing out the whole word aluminum. So one of the things we're going to work on in Chem 111 is understanding this notation or the symbols that we use in chemistry. Once you get an understanding of the logic behind it, I think you're going to find it's a lot easier than what you thought. Okay. And then AL is a symbol for an aluminum atom. Okay, again, symbolic, and it's microscopic. So, scientific method. Okay, all scientists gather and categorize information. We want to have an understanding of the world, and we continually question the world on what we think we know. And this method follows a specific process. And in the past, you've probably been taught a very formal step-by-step process. And science doesn't always follow that specific process, or any one specific process, but it follows a process that all scientists can agree that that's how to answer a question or to solve a problem. So in the scientific method, process of inquiry, hypotheses are possible explanations, and then we do experiments to prove or disprove those. So the graphic that you see on the right-hand side is your classic pattern that you make an observation, you ask a question, you form the hypothesis, you make a prediction based upon the hypothesis. And a lot of times you combine those two together, and then you do some sort of experiment to test the prediction. And sometimes you can't do an experiment, so you have to take evidence that's already out there. Then you analyze the results, and then decide whether the hypothesis is correct or incorrect. You report the results, and no matter what happens, whether the hypothesis is correct or incorrect, it's interesting. We try it again because we have to repeat. Okay, we have to repeat. So hypotheses that are unable to be disproven after several tests are eventually considered theories. Okay, and if a scientific theory holds up to constant experimentation, they are eventually considered laws, and that's a classic definition. In reality, theories try to explain why something's happening. Basically, laws are there to tell us what's happening. And so sometimes this difference between theories and laws can get a little bit confusing. So let's take a look on problem number 2 from the end of your chapter. It says, identify each of the following statements as being most similar to a hypothesis, a law, or a theory, and explain your reasoning. So falling barometric pressure precedes the onset of bad weather. So this is a law because it's consistently observed. If you notice, it's not trying to explain why the barometric pressure falls. It just says it falls before the weather gets bad. On B is a theory. All life on Earth has evolved from a common primitive organism through the process of natural selection. Not only is this a widely accepted explanation of the origin of species, can be controversial sometimes, but it's called a theory because it's trying to explain why or how something happened. Notice in A with the law, it just said this is what happens. In B, it's trying to not only say this is what happened, but this is how we think it happened. Okay. Letter C, my truck's gas mileage has dropped significantly, probably because it's due for a tune-up. This hasn't been tested yet, so this is just a hypothesis because it's a tentative explanation. And you would go ahead and you would do an experiment. Probably go and have the truck tuned up and see if the gas mileage gets any better. This is the presentation for section 1.2, phases and classification of matter. Okay. The objectives for this section is to define and recognize the states of matter, and then we're going to recognize and distinguish between pure substances and mixtures. So matter is anything having mass and occupying space. We covered that and talked about it a little bit in section 1.1. Basically, the 3 major phases are solid, liquids, and gases. And so here we have the 3 states of matter. If you notice, a solid has a fixed shape and volume. Liquid takes up the shape of the container, but it doesn't fill the whole container. And then finally, not only does the gas take the shape, but it completely fills the container. So let's take a look at these in a little bit more detail. A solid, again, like I said, had definite volume and shape. Its tightly packed particles, kind of like if you take a look at these ball bearings in the picture on this slide. There's some slight vibration. This vibration will be there as long as we're above 0 Kelvin. More on that story a little bit later on in this chapter. And basically cannot be compressed, because basically we've taken the atoms or molecules and smooshed them as close as we can to each other. So it's also considered a condensed state of matter. Liquids have a definite volume but a variable shape, so they take up the shape of the container, so the water in the bottom of the beaker. They're slow-moving particles, and they've gone from vibrating to now they're kind of sliding past each other, which is called flowing, and we'll talk more about that in chapter number 10, and we'll talk about the resistance to flow, or viscosity. That cannot be compressed, so the molecules are still really close to each other. So liquid is also considered a condensed state of matter. Gas or vapors, variable volume and variable shape. They basically expand out until they fill their container. Okay, the particles are very, very far apart from each other, and they're in rapid, random, and constant motion. So we're going to come back and take a look at the kinetic molecular theory, which is an important theory for chemistry, not only in Chem 111, but also explains a lot of things that are happening in Chem 112. Remember I said Chem 112, we're going to figure out why things are happening. In 111, we're going to take a look at what's happening. Okay, so you can see this smoke kind of spreading out. It'll keep spreading out until it reaches a limit where either the molecules completely spread apart, or with our atmosphere on Earth, the gravity has enough of a pull to and the molecules have enough of attraction for each other that they stay within several miles of the surface of the Earth. So what properties distinguish solids from liquids, liquids from gases, and solids from gases? See the number 9? That means this is question number 9 at the end of the chapter. Well, liquids can change their shape or flow. Solids can't. Remember, they're rigid. Gases can undergo large volume changes as pressure changes. Release the pressure on a gas and it'll keep expanding out. Okay, and liquids don't. They basically stay close to each other. Gases flow and change volume. So we're going to take a look at gas laws a little bit later on in the chapter. And again, solids do not. So the most interesting of these phases is gases, and we'll pretty much spend a whole chapter on gases because of how they're so unique from solids and liquids. So let's go ahead and we can classify matter. Okay, matter can be found solid, liquids, or gases, but they can be either pure substances or mixtures. Okay, pure substances can only be split apart by chemical methods. Pure substances are like sugar and salt and water. Okay, mixtures can be separated by physical means, and mixtures are combinations of 2 or more substances. And we're going to find several different ways of measuring this throughout Chem 111. So pure substances, we can start out with elements. They're found on the periodic table and can be atoms or molecules. So a couple examples, we've got O2 and Na and Fe. They can also be compounds that are chemically bonded elements. We're going to take a closer look at bonding in a couple chapters. This is chapter 3. Cannot be separated by physical methods. Okay, so a couple examples is water, sodium chloride, and caffeine. Again, all these are pure substances because it's only one substance that exists, but it's got a bunch of different types of atoms that are bonded to each other. Mixtures, physically mixed but not chemically combined, so we can separate them. Okay, they're a combination of more than one substance, and they can either be homogeneous or heterogeneous. We're going to look at a little bit of details on that in the next couple slides. So homogeneous mixtures, the same all the way through. Examples: Kool-Aid, coffee, brass. Okay, and we've got this rock candy on the right-hand side. That's really a mixture of water and sugar. That's got an interesting story to it. We'll take a look at that in the very last chapter. But there's actually some water mixed in with that, and depending on the amount of water depends on how hard that candy is going to be. So again, we'll talk a little bit more about that in detail in chapter number 10. Heterogeneous mixtures have different components are visible. Examples, muddy water, raisin bran, soil, or if you notice the cookies on the right-hand side, you can definitely see the Hershey Kiss, and you can definitely see the peanut butter cookie. So they're mixtures. You can see the different parts. So if we want to classify matter, what we've just gone over, we've got matter. If it's got a single thing, it's a pure substance. If it's got two or more that you can separate out physically, and if you can see them, it's heterogeneous all the way over on the left, homogeneous if they're the same. Again, with a pure substance, if it's not a mixture, they're all combined, it's either a single element or a compound. So how does a homogeneous mixture differ from a pure substance, and how are they similar? In question number 11. The mixture can have a variety of compositions. A pure substance has a definite composition. Remember, the pure substance is either a single element or elements that are chemically bound to each other. But both have the same composition throughout. So sometimes it's a little bit hard to tell the difference between the two unless you test them. How does an element differ from a compound, and how are they similar? Compounds can be broken down by chemical means, whereas elements cannot be decomposed by chemical means. That'd be a nuclear reaction if we're breaking them down. That's for Chem 112. They're similar in that they both have properties associated with matter. They have specific properties that'll identify and help us classify them. So it says classify each of the following as an element, a compound, or a mixture. Well, I think copper is pretty obvious. It's an element. You can find copper on your periodic table. Okay. Nitrogen, again, is an element. Interesting thing is when we go to write it, we write it as N2. We'll talk about some atoms that are in their elemental form. They're actually diatomic, and we'll talk about why in a couple chapters. Air is a mixture. Okay, technically it's a homogeneous mixture unless it's polluted and you can see other things in it. And then a substance composed of molecules, of each of which contains two iodine atoms, and that's that diatomic thing, or diatomic elements, which is a relatively new thing that's been showing up in chemistry textbooks. I say new, but for about 10 years, when I was in high school, we didn't consider that iodine as combined together as an element, but now that we do, it makes a little bit more sense, a little bit easier to understand some of the things that we talk about in higher level chemistry. Number 19, how are molecules and oxygen gas, the molecules and hydrogen gas and water molecules similar, and how are they different? Well, in each case, the molecule consists of two or more combined atoms. They differ in the types of atoms, and those different types of atoms are going to give them different properties and different characteristics. And we're going to be taking a look at some of those a little bit about the second half of Chem 111. Okay. As we drive, number 21, as we drive an automobile, we don't think about the chemicals consumed and produced. Prepare a list of the principal chemicals consumed and produced during the operation of an automobile. Well, what I've come up with is gasoline. It's a mixture of compounds. A lot of people think it's octane or one molecule, but it's actually a mixture of compounds. We add oxygen to it. Sometimes nitrogen from the air is consumed. That's when we get the nitrous oxide, and that's what the catalytic converter is trying to get rid of. But for the most part, we get carbon dioxide and water are the principal products. Sometimes we get a little bit of carbon monoxide and nitrogen oxides, and again, that's what that catalytic converter is used. It's trying to reduce the nitrogen oxide. Carbon monoxide we try and eliminate by making the car as efficient as possible. And I got a sample problem a little bit later on in a later chapter that's going to show we're going to chemically calculate it, but now your car will electronically calculate that ratio that we're going to take a look at. Okay, so this is section 1.3, physical and chemical properties. Basically, the objective of this is to distinguish between physical and chemical changes, but in order to do that, you have to know something about the physical and chemical properties of the substances to begin with. So we take a look at physical properties. It's any quality that can be observed without changing the chemical composition of the substance. Okay. So if you look at the graphic on the right, you'll see that the ice is melting into the cup, but we start out with solid water and we end up with liquid water. Okay. So some of the properties we can take a look at is mass and density and color. We can also take a look at texture, magnetic, malleability. Can you pound something into a shape? Ductile. Can you stretch it into a wire? Freezing point and melting point. The ones that are bolded and reds are the ones that we're pretty much going to be concentrating on in Chem 111. We don't really take a look too much. We'll talk a little bit about malleability and ductility, but the other five are the ones that we're basically going to see over and over again in Chem 111. So physical properties, we can use several different methods to purify substances. Okay, one is chromatography, distillation, sublimation, and solubility. Chromatography, there's a variety of ways of chromatography, and we'll talk about mass spectrometry in chapter number 3. Distillation, there's a picture here. It's separating it out by different boiling points. Sublimation is when a solid turns directly into a gas, and we'll talk about conditions for that. We really won't talk about that until chapter number 10. And then solubility. And one of the ways we can get different substances is to create what are called precipitation reactions, because different substances have different solubility in water. So we can take advantage of that in order to purify or pull different substances out of a solution. A physical change is a change that does not alter the chemical composition of the substance. So we can cutting and melting and freezing and boiling and dissolving. Okay. The interesting thing is cutting and dissolving basically are the same thing as taking a substance and making it smaller. Cutting, you're just breaking it, or grinding is also, we could put with cutting, you're making it from bigger to smaller and smaller pieces. Dissolving is actually taking those small pieces and separating them out with something in between of them. Typically it's water. We take salt or sugar and drop it into water. We can get the salt ions or the sugar molecules to break down into smaller ones and separate from each other. Chemical properties are any quality that can be observed when changing the composition of the substance. Classic things we'll hear about is flammability, reactivity, oxidation. We have a whole chapter on oxidation and reduction in Chem 112. In chapter number 4, we'll take a look at it in a little bit of detail to kind of give us a little bit of background of what's happening. And then in Chem 112, we try and determine why it's happening and come up with some unique ways of measuring it. Okay, oxidation, if you notice, is like that flame in the lower right-hand corner. Okay, oxidation is like this rusting of this anchor chain. So if we take a look at question number 1, yeah, sometimes I'm going to skip around a little bit because sometimes I think an earlier question goes better with a later section. But for the most part, they're in chronological order at the end of your the chapter in your textbook. It says, explain how you would experimentally determine whether the outside temperature is higher or lower than 0 degrees Celsius without using a thermometer. Yeah, it doesn't have to be very complex. Basically, if you place a glass of water outside, if the water freezes, the temperature is below 0 degrees Celsius. Come on, let's all admit that when we were in school, we checked the weather forecast to make sure if it was going to precipitate, whether it was going to be below 32 degrees Fahrenheit, because we knew then we were either going to get freezing rain or snow and we'd get the day off from school. So number 26, it says, classify the 6 underlined properties in the following paragraph as chemical or physical. And I've already put these in here, so we don't have to play with animations. But if you'll notice, fluorine is a pale yellow gas. Okay, so we're looking at the pale yellow. And so that's a physical. Reacts with, so there's a reaction, so that's chemical. We've got the melting point, so that's a physical property. The boiling point is a physical property. If something burns or it oxidizes, like the metal burn in fluorine, that's chemical. It's a chemical change. And then 19 grams of fluorine will react with, and it's talking about react with, so that's a reaction, so that would be chemical. Number 28 wants us to classify each of the following changes as physical or chemical. Coal burning, that's oxidation, so it's chemical. Mixing chocolate syrup with milk to make chocolate milk, that's physical, that's just a mixture. And if you stir it well enough, then it goes from a heterogeneous mixture to a homogeneous mixture where it will look the same throughout. Magnetizing of a screwdriver, that's a physical change. And some people may argue maybe it's chemical, but basically all you're doing is just rearranging the electrons around the screwdriver so that you got more one end than the other. And we'll talk a little bit more detail about that. I think that comes up in chapter number 9. Extensive and intensive properties, okay, and how we classify these physical properties. And we'll talk about them, but I don't concentrate a whole lot on them. Extensive properties are basically things that are on the outside. You look on the outside in. So if you've got an object, you can look on the outside, see how much mass, how long it is, its volume. An intensive property is as if you're inside of it. So if you're inside of it, it's not going to change. So that would be density, the temperature, the color. Number 32 says identify them with properties of either extensive or intensive. Volume is extensive. You're looking on the outside to find out how much you have. Humidity is intensive because you're inside like a humid room, okay, humid weather. Boiling point is intensive, okay. Again, all particular substances are going to have the same boiling point. We can use that to identify different substances. One thing that's used in organic chemistry a lot is you find the boiling point of the substance, and then you can eliminate several 100,000 molecules that it can't be. 33, the density of a substance is an intensive property that is defined as a ratio of mass to its volume. Considering that mass and volume are both extensive properties, explain why the ratio density is intensive. Being extensive properties, both mass and volume are directly proportional to the amount of substance under study. So by dividing the two or comparing the two, what we find is that ratio is independent of the amount. It always stays the same. So we go from two things that can change, but when we combine them together, it forces them to stay the same, and we end up with a ratio. So we can use density, and again, that's one of the things we can use to identify substances. If we know the density of an unknown sample, we can eliminate hundreds of thousands of compounds for things it can't be. This is section 1.4 on measurements. What we're going to do is the objectives are to perform calculations using numbers with SI units, and we'll talk about the SI units. Then we're going to take a look at converting between base units and units containing prefixes. And then we're going to also take a look at the 3 different temperature scales and be able to convert between them. So the units of measurement, one type of scientific observation, of course, is a measurement. This is where we get into the numbers. Contains quantitative and qualitative parts. Not only does it have a number, but it also has a unit. Notice in our examples, it's 1.2 meters, 45 years old, and 3.0 times 10 to the 8 meters per second. So this is a little bit different from your math class in that now we have units on these things and we're actually measuring quantities. We have to be careful with our numbers. So our SI units, basically there are 7 of them, and these are the things that we measure everything in the world, or at least scientists do. The mass is the kilogram. We're going to use gram for convenience. Time is the second, not the minutes, because minutes is a hassle because there's 60 seconds in a minute. Temperature is the Kelvin, and we'll talk about why it's called the Kelvin and when we get to temperatures. Electric current is the ampere. We won't do a whole lot with that in chemistry. That's more for physics. The amount, the mole, that's the chemistry thing. We'll talk a lot about moles in chemistry. Luminous intensity, or is the candela, that's more of a physics thing. And then the distance is the meter. You'll notice there's no volume listed on here. So what we're going to do is we can use any of these units and we can derive all the other units that we use to measure in science. Again, what I've done is blocked around the ones that we're going to use more often than not. The reason I didn't block in the kilograms is we're basically going to use the grams as a convenient unit. So we need to talk about mass versus weight because you're going to use an electronic balance, not a scale. Weight is basically the gravitational attraction, and mass is the amount that matter that something has. And interesting, we got a picture of the Earth and the Moon. When you go to the Moon, your weight is 1/6. So if I take a 180-pound astronaut on the Earth and launch into the Moon, basically he has a mass of about 30 pounds. And if you've ever watched any of the movies or film clips from when we land on the Moon, you'll see that the astronauts kind of bounce around because there isn't as much gravitational pull holding them to the surface. Now, did the astronauts lose any mass going there? No, it's still the same amount of mass. Maybe gain or loss a little bit depending on calorie intake and stuff. But as a general rule of thumb, they have the exact same mass. It's just that gravitational attraction. You'll notice the Moon is about 1/6 the size of the Earth. So that's why there's only 1/6 the gravitational attraction. We can also derive units. It's 2 or more units to have a new type. Speed, meters per second. Density, which definitely is probably a familiar one, is grams per milliliter. Well, if you'll notice, we didn't have any volume on our list of SI units. So milliliters is actually the derived unit. So if we have a large piece of jewelry, it has a mass of 132.6 grams. A graduated cylinder initially containing 48.6 milliliters, then dropped into the graduated cylinder and the water rises to 61.2 milliliters. So what we're going to find is to find the density is we need the mass over volume. So the density is that 132.6 grams, which was an extensive property, divided by the difference in the volume change, which is the volume of the jewelry, and we end up with 10.5 grams per centimeter cubed. There's an interesting story behind this because with Archimedes, what he did is he was looking at gold, and he realized that the crown of the king, when dropped into a bathtub, should displace less water than something that was less dense. And when he dropped the crown into the tub actually overflowed from what he calculated, and he realized it wasn't the same density and it wasn't gold. What we're going to find is our jewelry is silver because the silver is 10.5 grams per centimeter cubed. The other interesting story is once Archimedes figured it out, he yelled Eureka, and as the story goes, he ran down the street naked because he'd figured out that the king's crown was not pure gold. Again, it's an urban legend. How much of the story is true, who knows, but it's always a fun and interesting story anyways. 36 says indicate the SI base units or derived units that are appropriate for the following measurements. The length of a marathon race is in miles and yards, and so it's measured in meters would be the derived unit. We basically use kilometers. You've probably heard the term 5K, and a 5K is equal to about 3.1 miles. And for those of us who are runners, it becomes very easy to convert between kilometers and miles now that we know a 5K is equal to about 3.1 miles. Mass of an automobile is going to be measured in kilograms. Again, we're using the SI units. The volume of a swimming pool is going to have to be a derived SI unit, so it's going to be in cubic meters. Remember, the meter was the unit of length. And then the maximum temperature at the South Pole on April 1st, 1913, we would use Kelvin, okay, from the SI units. So now on section 1.5, measurement of uncertainty, accuracy, and precision. In the previous section, we talked about SI units and that measurements always have a number and a unit. Well, because we're measuring things or objects, we need to be careful about accuracy and precision. And one of the ways to make sure we have the most accurate and precise measurements is to have the correct number of significant figures. So significant figures are all known numbers and one uncertain. In lab, we read from the bottom of the meniscus. Here we've got a graduated cylinder. And this would read, if you notice, the bottom of the meniscus is just touching that big long line underneath the 20. So we would read this as 20.00 milliliters, okay, because it's not 20.1, okay, which would be the small line just above, or sorry, just below. And so if you notice, this is going to be 21.00 milliliters. This isn't a graduated cylinder. It's actually a burette because it's reading down. And burettes actually measure how much you've delivered, not how much you've filled them with. So if you'll notice, when we go to record off of our equipment, we always measure out to 1 decimal place past the markings that are on the piece of equipment. Notice that this can measure to the 0.1 milliliter, so we can measure it to the 0.00 milliliters because we could estimate in between. So we need to use significant figures to make sure we're recording, not only recording our measurements correctly, but also so that when we go to do calculations that they stay accurate and precise. So there's some rules in order for writing down numbers or figuring out which digits are significant, and then we'll use those that are significant for figuring out how to record answers to calculations. So the first rule is all non-zero numbers are significant. What we're assuming is somebody wrote the measurement down correctly in the first place. The next set of rules are for zeros, okay, and the zeros are our problem children. Okay, leading zeros are never significant because they're just placeholders. Okay, if you take a look at our example, 0.02 tells us to put the 2 not in the ones, not in the tenths, but the hundredths place. In our bottom example, 0.001 tells us to put the 1 not in the ones place, not in the tenths, not in the hundredths, but in the thousandths place. So leading zeros are never significant because basically they're just placeholders. Zeros in the middle of a number are significant. Okay, sometimes they're called trap zeros because they're actually part of the measurement. Remember our 20.00 from our burette. That zero in the middle, the zeros, are actually part of the measurement. If you'll notice our 0.04002, we don't count the leading zeros, but we count the ones in the middle, so we get a total of 4 significant figures. Trailing is the issue. Before, never. In the middle, always. At the end, we need some way to say, yes, those zeros at the end of the number are significant. And what scientists have figured out is they use a decimal point or a period as the designator. So if you take a look at our examples, the difference between 100 with a decimal point without a decimal point is the difference of 1 or 3 significant figures. What that means that decimal point is someone actually measured all the way down to that decimal point, or in the 0.200, they actually measured to the decimal point and passed, or units that are smaller than 1. So how many significant figures are in each of the following measurements? Well, the first one's pretty simple. It doesn't have any zeros, so it's going to have 2 significant figures. The next one down, the 3,001 grams, the zeros in the middle are always significant. So we end up with 4 significant figures. Now we're going to start mixing and matching the rules. If you'll notice in our meters cubed, we have 2 zeros at the beginning, so we don't count those. The 0 at the end counts because there is a decimal point. It does not matter where the decimal point is. If there's a decimal point, then we count the zeros that are at the end of the number. So this has 3 significant figures. The nice thing about scientific notation is if it's done correctly, all the digits before the multiplication sign would be considered significant. The thing is, if you notice, there's no 0, so we wouldn't have to worry about that anyways. And then our last one, 560 kilograms. Someone got lazy in their measurement because they only measured out to 10 grams. So with 10 kilograms, which would be 10,000 grams. So that's only going to have 2 significant figures because that 0 doesn't count because there's no decimal point. So how many significant figures are contained in each of the following measurements? A, we've got 3. Then for scientific notation, all the numbers before the multiplication sign, or there's no 0, so it's only going to have 1. That's not really a good measurement. C, if you take a look, it's got 7. Those zeros are trapped. And G, which is a classic type measurement we have in chemistry, it's going to have 4 significant figures because the zeros before are not significant and the zeros after are. And so we end up with 4 significant figures. We also have a category called exact numbers that contain infinite significant figures. These are either by counting or by definition. You got 5 pencils in a box. You can just count them 1, 2, 3, 4, 5, or 5 people in a room. 1 meter is exactly equal to 100 centimeters. Technically, you've counted out 100 of them and put them together to make a meter. But our metric conversions have an infinite number because by definition, we can just add a decimal point to the end of the 100 and keep adding zeros. Also, there are exactly 12 inches in 1 foot. Okay, so some of our numbers contain infinite significant figures. What that means, it just doesn't affect how we're going to record our final answer. So as I said, indicate whether each of the following can be determined exactly or must be measured with some degree of uncertainty. Okay, the number of eggs in a basket can be counted, and counting numbers are considered exact. The number of gallons of gasoline necessary to fill an automobile gasoline tank is uncertain, because typically if you look in an owner's manual, let's say it takes 19.1 or 18.9 or 20.3, okay? And the mass of a textbook is uncertain, okay? Because you would put it on a balance, you would measure it out, and it would weigh, 2.36 kilograms. Notice the key thing here with the eggs is we can count, and counting numbers are always exact. And then we'll have some conversion definitions. So the reason we have significant figures is because we don't just write down them, we usually do something with them. So in addition and subtraction, the answer cannot have more digits to the right of the decimal point than any of the original numbers. This is the idea of a chain is only as strong as its weakest link. So if you look at our top example, the top number said the person measured all the way out to not only the 10, 100, but to the thousands place. But the plus 1.1, that person only went to the tenth place, and everything past that's going to have error. So what we're going to do is we're going to round off our number. Yeah, that's what significant figures is about. It's about rounding our answers when we type them into the calculator. Okay, it's no more complicated than that. And so what this tells us in our first example is we have to round off to the 90.4 because we can't go past the least number of digits to the right. If we take a look at our second example at subtraction, and we follow the exact same rule. So we need to round off to 2 decimal places. And if you'll notice, it's 0.786. The 6 is higher than 5, so that's going to make the 8 a 9. And so we're going to round off to 0.79. So you just learn the whole trick of significant figures. And that significant figures is just about how do I round my answer when I go to record it. Multiplication and division. This is why we were finding the number of significant figures in a number. You'll notice 4.51 has 3 significant figures. So we're going to round to 3 significant figures. And we end up with 16.5. We're going to round to the smallest number of significant figures. That 3.6666 definitely has more than 3. You add it up, it actually has 5. Division, same thing. Smallest number of significant figures. 6.8 only has 2, which is definitely, we can just eyeball and see is less than the 112.04. So we're going to have to round to 2 significant figures. So we're going to start at the 6, because remember the preceding zeros, the zeros before, are not considered significant. So we're going to round it to 0.061. So we want to answer the following to the correct number of significant figures. So if we take a look at number 1, we're going to take 3 digits times 2 digits. And we end up with 2.48 in the calculator. Well, we can only record our answer as 2, because there's only 1 significant figure in the 0.2. On number 2, we're going to add them together. If you'll notice, when we add them together, the 0.4 only goes 1 decimal place to the right, so we have to stop there. So we end up with 40.6. Number 3 is going to get ugly, because we got 100 with no decimal point times 14. We would think it's 1400, but we can only record it as 1 significant figure. And now we're going to say 1400 is the same thing as 1000. We got to really be careful with our numbers in chemistry. And then 100 divided by 17, 4.58823, and keeps going in your calculator. Again, we only have 1 significant figure because of the 100, so we end up technically with an answer of 6. So again, scientific notation useful for dealing with large or small numbers, which is probably what you've been told about in the past. Contains a coefficient in the power of 10. But the cool thing is if written correctly, all the numbers in the coefficient are significant. So what we find is everything before the multiplication sign is considered to be significant. So it says, convert the following to scientific notation. Assume 3 significant figures for each example. Okay. So, and your calculator can handle scientific notation, and you need to make sure, we'll talk about this in a couple of future chapters, and you may have to Google your calculator or look up the owner's manual and make sure you're putting it in correctly, and make sure it matches up to the answers that I'm getting. But the one general rule of thumb is the exponent that's found on the 10 is going to be greater than 1 if the number's greater than 1. Or that exponent is going to be less than 1 or 0, or negative if it's less than 1. So if I take a look at A, I'm going to have an exponent that's going to be greater than 1, and I just need to figure out how far to move the decimal point. So I'm just going to count how many spaces over to get the decimal point between the 6 and the 7, because scientific notation always starts with a number in the ones place, a decimal point, and then the rest are the number of significant figures. This problem is pretty easy because it only wants 3. So we're going to do 6.7, and I have to move the decimal point 6 places back in order to put it between the 6 and the 7. So that's where I get 10 to the 6. On the next one, I'm going to move it 4 places to the right, and I only need 3 significant figures. Be careful that 3 is next to a 5, so the 3 is going to round up to a 4. If you were to put in 1.23 times 10 to the minus 4th in your homework problems that you're going to do through Blackboard, I'll give you credit for the answer. It's designed so that there's some flexibility when you go to put in. Usually what I've done is I've allowed plus or minus 1 significant figure for each answer. C is going to become 6.01 times 10 to the minus 1. And 3.33, we're not going to worry about writing down the times 10 to the 0. So it says express each of the following numbers in scientific notation with correct significant figures. So A is going to be 7.110 times 10 to the second. And you go, why would I write a number that small? Because when we put it in scientific notation, we know definitely for a fact all four of those numbers are significant. And you'll see that in some of the problems that we'll work through. You'll go, well, why did he write 1.2 times 10 to the second? That's 120. Well, we know it's 120 with only two significant figures. Our 2.39 times 10 to the minus 1. 9.0743 times 10 to the fourth. And we end up with 1.00 times 10 to the fourth. Now it says round off each of the following numbers to two significant figures. The reason I put this problem is to remind us that the only reason we worry about significant figures is to know where to round off our number. We'll find out why in just a second. So A is 0.44. C is 27. Again, we'll round it to two significant figures. E is going to be 1.5 times 10 to the minus third. Number 53, it says perform the following calculations and report each answer with the correct number of significant figures. So if I take 628 times 342, I should end up with 2.15 times 10 to the fifth. C, I should end up with 2.08, three significant figures. And finally, E, when I go to add all these together, the 14.98 goes out to two decimal places to the right, but the 27,340 only goes to the 100 place. So our answer can only be 27,440 because that 27,340 only goes out to the tens place. Why do we worry about significant figures? Because of this thing of accuracy and precision. Accuracy is measuring how close to the true value we get something. So if you take a look at our dartboard, okay, precision is subsequent measurements are close to one another. So accuracy is getting the correct answer. Precision is getting the same answer. If you take a look at our two classic dartboards, and the one on the left, if you'll notice, there's high accuracy because they're pretty much getting close to the bullseye or in the bullseye, but they're not really close to each other. The one on the right, yeah, we're getting them all close to each other, but they're not where we want them to go. The one on the right is the one that has a tendency to get scientists into trouble. We keep getting the same answer over and over and over again, and then we assume, well, if it's the same answer, it must be the right answer. And that's not always true. We have several ways we can measure that. So here's our dartboards again. And it says, consider the results of the archery contest shown in this figure. Okay, so A, which archer is the most precise? So we're looking for the one that's getting their arrows into the bullseye. So that'd be archer, precise. I take that back. Precise is the ones that are close to each other. Now the one that's the most accurate is the one that is closest to the bullseye. So that's archer W. Who is both least precise and least accurate? Well, that looks like how I would shoot the arrows. And that's going to be archer Y because he didn't even make it onto the target. Number 56, it says, classify the following sets of measurements as accurate, precise, both, or neither. Because typically in chemistry, we're not throwing darts. Even though we do pencil darts in my face-to-face class to figure out where the electrons are, we can simulate some data. But if we take a look at A, if you take a look at our data, if you'll notice, they're not even close to each other. So what we're going to find, it's neither accurate nor precise. If we take a look at testing the volume of a batch of 25 milliliter, we'd expect the answer to be around 25. You'll notice, yeah, they're pretty precise. They're getting 27 all the time, but nowhere close to that 25. So I'd say they're precise, but they're probably not accurate. Now, if we want to determine the purity of gold, look at all these 99.999 and only the last digit, which is the 10, 100, 10,000ths place. I would say that this is probably both accurate and precise. Error is the difference between the true value and the measured value. So what we're doing is we're looking at accuracy. Okay, scales reading too high, gas gauge is not calibrated, spilling after measuring the liquid in your graduated someone in the lab are all examples of where you can lose accuracy. Could still end up the same precision because you could end up reading the same thing, getting the same number over and over again, but it's not getting the accurate value or the correct value. So one of the ways to measure that is to calculate a percent error. Percent error is going to tell us how close numbers are to the accepted or how accurate they are. Precision tells us how close they're to each other. We can do an average deviation. We do that in the face-to-face lab. This is section 1.6, the mathematical treatment of measurement results. In the previous section, we'll take a look at accuracy and precision and specifically significant figures. And we have to worry about those because now our numbers have units. In this section, we're going to figure out how to convert from one unit to another. So dimensional analysis is a way to convert between one unit and another. We start with a given. We consider all equalities or conversion factors. Then we plug in so that the units cancel each other out. And this sounds complicated, but once you learn the pattern, we use this over and over and over again in chemistry and also physics. That if you understand this concept of getting units to cancel out, there's a variety of problems you can do using the same method. You just need to go find what the conversion factor is. And in today's day and age, finding a conversion factor is relatively easy, especially if you have access to the internet, because you can pretty much find the conversion factor for almost anything you're interested in, unless it's something brand new that nobody has ever heard of or thought of before. So the most common conversions we'll run into include the following. And notice this is table 1.3 from in your textbook. And no, we're not going to deal with all of them. We're pretty much going to deal with that middle section, the milli, the centi, the deci, and the kilo. And I would expect for you to be familiar with those. The micro, the nano, pico, femto, giga, mega. When we need them, we'll talk about them, and I'll give them to you in the problem. So there's some common conversion factors between English and metric system. Table 1.6 in your textbook gives those conversions. Again, when you need them in a problem, I'll give you the conversion factor into the problem, so we don't have to worry about spending the time going and looking them up. Some of your problems on the homework, you might have to go look them up to go find the conversion factor. But definitely on a test or on an exam, I will give you the conversion factor because those are timed. So is 1 liter about an ounce, a pint, a quart, and a gallon? I remember when I first started teaching chemistry 30 years ago, I would have to teach about the metric system. Well, we're all fairly familiar with the metric system because we buy 2-liter bottles of soda and we buy gallons of milk. So this question is about, do you have an idea of what the relative size? And 1 liter is about a quart. So we have some idea of the volume we're talking about. Liter is a pretty large amount of volume for a chemist, unless I'm an industrial chemist working, and then I'm probably looking at the kiloliter or the megaliter or 1,000,000 liter mark. Is a meter about an inch, a foot, a yard, or a mile? And hopefully about a yard comes to mind for you. So now what we need to do is we need to be able to do some dimensional analysis and convert from one metric unit to another. And I know some of you can move the decimal point, and I don't want you to do that because I'm going to teach you a method for solving problems in chemistry that we will use over the next 5 chapters. So you can either learn how to do hundreds of different types of problems or learn one method and how those hundreds of types of problems can use that one method to solve them. And yes, that is the easier way to go. So you're going to hear me say over and over again, if you don't know what to do, what I'm going to ask you to do is you're going to write down the number and the unit, multiplication sign, division bar. Haven't done anything complicated yet. So I don't want centimeters, I want meters. So if you remember in your math class, if you want to get rid of something, you multiply by its reciprocal. So if I want to get rid of the unit, if it's in the top, I'm going to put it in the bottom. If it's in the bottom, I'm going to put it in the top. Right now, we're just going to concentrate. I've got it in the top. I want to get rid of it, so I'm going to put it in the bottom. I want to find meters, because I've gotten rid of centimeters. And now what I need is I need a conversion factor. And the conversion factor for centimeters to meters is there are 100 centimeters in a meter. Or there are 10 to the minus second meters in a centimeter. I forgot, your book likes to use the 10 to the minus second or the unit numbers in front of the meters. So we've got 83 times 10 to the minus second. Notice this is on the top, so it's a multiplication problem. Numbers on the top are always multiplication. Numbers on the bottom are always division. So this says take 83 multiplied times 10 to the minus second. If you have a TI series calculator, this is really easy because you're just going to type in you're going to type in 83, multiplication sign, 10, hat or caret button, -2, hit enter. And you're going to end up with 0.83. Okay, my answer should only have 2 significant figures in it because I only started with 2 significant figures. That 10 to the minus second is a conversion factor, and conversion factors are exact numbers and an infinite number of significant figures. So our next one is convert 459 liters into milliliters. So I'm going to take 459 liters, multiplication sign, division bar. I want to get rid of the liters. I'm looking for milliliters. And my conversion factor is there are 10 to the minus 3 liters in a milliliter. So I'm going to take 459 divided by 10 to the minus 3 is in the bottom, and I should end up with 459,000 milliliters. Please go back and make sure you can do this in your own calculator. If not, please ask. Now I'm going to convert 0.7824 milligrams, and I've got 4 significant figures, into grams. Write down the number, the unit, multiplication sign, division bar. Put milligrams in the bottom, because I want to get rid of milligrams. Put grams in the top. And there are 10 to the minus 3 grams in a milligram. It's on the top, so I'm going to use multiplication. And I should end up with 0.000784 grams, or 7.824 times 10 to the minus 4th in scientific notation, which would be more appropriate. But because Blackboard and its testing system, when you go to do your homework, I'm going to tell you to just put it in normal notation. Or what I'll do is I'll ask you to put in the significant digits, multiplication sign, and I'll give you the 10 to the whatever power. You'll see that as you work your way through the problems. Let's take a look at the temperature scale. Fahrenheit is seldom used. Okay, Celsius the more convenient because of the 100 unit scale. And then Kelvin is the SI system, or the one that's used for the SI system. So if we take a look, the freezing point of water is marked on this and the boiling point, because Fahrenheit and Celsius basically took their thermometers and they were measuring the freezing point of water and the boiling point of water. Fahrenheit then actually took water and he put salt and ice in it and measured as far as it would go down, and he said, well, that's 0 degrees Fahrenheit, so that's where we got the 32. It's a colligative property. More on that story in chapter number 10. Celsius decided to go a little bit simpler. He said, I'm going to just start with the freezing point of pure water and the boiling point of pure water at sea level, and I'm going to break it into 100 units. And so we have a conversion factor, or a formula to convert from Fahrenheit to Celsius and Celsius to Fahrenheit. It's not an easy conversion. We don't do it a whole lot. I'll show you how to do it, but we're not going to do it a whole lot because we don't really use the Fahrenheit scale that much. And even in the medical profession, there are electronic or digital thermometers. You just push a button on it, and usually the thermometer will flip back and forth between Fahrenheit and Celsius. So we want to convert 172.9 degrees Fahrenheit to degrees Celsius. So our formula is Fahrenheit minus 32 times 5 over 9 will give us the Celsius degree. And this becomes an algebra plug and chug into the equation type problem. And so we end up with 78.3 degrees Celsius. The Kelvin scale, what Kelvin tried to do is, remember Fahrenheit, I told you, he put salt water and tried to get as cold as he could. Well, Kelvin wanted to find what is the coldest temperature you can have. So he wanted an absolute scale, and through experimentation, and the online students, you'll do this earlier, it's actually the second lab they're going to have you do, is you can experimentally find absolute zero, and it's minus 273.15 Celsius. And this has actually changed within my career, because when I was in high school it was 0.12. So it's actually changed by a factor of 0.3. The nice thing is it's relatively easy to convert from Celsius to Kelvin. It's just a factor of 273.5, and the Kelvin always has to have the higher temperature. Easy to remember, if I assign a number, 1 is A, 2 is B, 3 is C, 4 is D, and so on, the K is going to have the higher number. So no matter what you do with the 273.15, the K's got to have the higher number. So you add the 273.15 to the Celsius to get the Kelvin. So I want to go 212.00 Kelvin to Celsius. The Celsius needs to be smaller, so I'm going to subtract. And I end up with negative 61.15 degrees Celsius. Please be careful with the negative numbers. For 47.25 degrees Celsius, add the 273.15, and we end up with 320.40 Kelvin. So in problem solving, we need to consider the starting and ending units. Make a list of equalities or conversion factors going to be used, because sometimes we're going to need more than one. And that list, you can either write them down or you can do them mentally. Make sure your units are written so they cancel out, and that's really key. That's really key. So what we're going to do is we're going to take a look at some problems and see how to use this idea of problem solving. So 63 says, how many milliliters of soft drink are contained in the 12-ounce can? This is a convenient answer to know. So 12 ounces. We go to the table that's found on page 14 in your slot notes. We get rid of ounces, and we're going to find there's 29.6 milliliters per ounce. We're going to multiply these two, and we end up with 355 milliliters. If you look on the outside of a soda can, you'll see it says 355 milliliters. I know this one off the top of my head because I've used soda cans in a variety of labs throughout my career, and I've needed to know what the volume inside of the can is. Number 69, medical laboratory tests are run 5 microliters. So we want to know milliliters. So again, you go to page 14. Get rid of the microliters. And there are 10 to the minus 6 liters in a microliter, or there's a million microliters in a liter. And if we multiply these two, we'll end up with liters, but I want to know the volume in milliliters. So I'm going to get rid of the liters, put milliliters on the top. There are 1,000 milliliters in a liter. And we end up with 5.0 times 10 to the minus 3 milliliters. A long ton is defined as exactly 2,240 pounds. What is the mass in kilograms? Okay, 2,240 pounds. I'm going to get rid of 2.2046 pounds in a kiloton. I'm sorry, in a kilogram. And then end up with 1,020 kilograms, or basically a metric ton. Number 6, it says make the conversion indicated in each of the following. The area of the state of Oregon is miles squared. This is an interesting in that we're squaring and cubing our units. And I used to have a hard time with these until I figured out the simple trick. First of all, we've got 96,981 miles. We want to convert that to kilometers. So I'm going to get rid of miles. And there's 0.62137 kilometers in a mile, but because this is squared, I'm going to square my conversion factor. I used to do all sorts of weird stuff to come up with the answer until it finally hit me. If I square the unit, I square the conversion factor. And now my calculator can take care of it. So we're going to end up with 25,000, actually it's going to be like 25,1118 kilometers squared. The estimated volume of the oceans is in miles cubed to cubic kilometers. Again, that 0.62137, but now we're going to cube it instead of square it. We end up with 1.4 times 10 to the 9th kilometers cubed. That top one is actually 25 million. I'm missing the comma between the 8 and the 2. Calculate the density of aluminum. This should be pretty straightforward. Hopefully you've seen the formula for density before. D equals M over V. We're just going to put the mass over V, and we end up with 2.70 grams per centimeter cubed. That 2.70 grams for aluminum, that shows up every now and then. It's kind of convenient to kind of have that in the back of your head. Okay, so what is the mass of 6 centimeters cubed of mercury? And we're given a density. So we're given a conversion factor, and if you don't know what to do, let's start with the one with the single unit on it. Multiplication sign, division bar. We're going to get rid of those centimeters cubed because we're looking for mass. So if I put grams on the top from the conversion factor that I'm given, it says it's 13.5939. Both numbers are on the top, so it's multiplication. And I end up with 81.6 grams. Number 91, to calculate these volumes, I've got 25 grams of iodine, okay, given density. 25 grams, multiplication sign. I want to get rid of the grams because I'm looking for volume. Volume is in centimeters cubed, which is the same thing as a milliliter. And then with 5.1 centimeters cubed, again, two significant figures because I only started out with 25 grams. On number 96, it says convert the temperature of dry ice into degrees Fahrenheit and Kelvin. So if you notice, what I did is I converted Celsius to Kelvin first, because that was the easiest. And then I use my formula, and I end up with a minus 81 degrees Fahrenheit. That's kind of weird the way the graphics work. And that ends chapter number 1.